This video covers momentum, two-dimensional collisions. Remember in the last video, one of the things we talked about is that momentum is conserved in all directions. So remember that if a collision is elastic, you want to use the conservation of kinetic energy as a second equation. So for these problems, it's going to be very important that you use a lot of subscripts to identify all the objects and indicate initial and final velocities. Now, I've been using knots and discontinuing the F's for finals, but if you think that'll help you, that's okay. You can use that instead. Now, when we say the momentum is conserved in all directions, you need to make sure that you write momentum equations for the x direction and then write momentum equations for the y direction. You don't want to combine the two together. Now, here are the two equations. You don't need to rewrite them, but when we come to a problem, it's going to be important that you write them out. But here you don't need to. So this problem says a 1,500 kilogram car traveling east with a speed of 25 meters per second collides at an intersection with a 2,500 kilogram van traveling north at a speed of 20 meters per second. Find the direction and magnitude of the velocity of the wreckage after the collision, assuming the vehicles undergo a perfectly inelastic collision. Again, perfectly inelastic means that they aren't going to stick together. So here, we can write our momentum equations for both directions. So in the x direction, we have our momentum of our first object, which is we'll call him M1. M1 V1 naught plus 0, since our second car has no momentum in the x direction. And that's going to be equal to M1 plus M2 times our velocity in the x direction final. Now, here you can add x subscripts everywhere, but that might make your equation look a little bit more messy than it needs to. So I went ahead and labeled it as x over here at the beginning. In the y direction, we have our momentum of our second object, and it has an initial velocity. The first object has no initial momentum in the y direction, and again, we know that they will be colliding. So these are our two equations for our momentums in both directions. So for the first one, we can solve for our velocity in the x direction, and that is M1 V1 naught over M1 plus M2 is equal to our velocity in the x direction. When you plug in all of your numbers, you should get a value of 9.375. I'm going to go ahead and carry all those numbers right now. For this momentum in the y direction, again rearranged, I get M2 V2 naught all divided by M1 plus M2 is equal to our velocity in the y direction. Again, this is, once I plug in all my numbers, you should get a number of 12.5 meters per second. Now, the important thing after this is to recognize that what we solved for is our velocity in the x direction and our velocity in the y direction. What the problem is asking for is our resultant velocity. So in this case, it is the hypotenuse of this. The hypotenuse of our triangle that we create. So to get that, it is the Pythagorean theorem of 12.5 squared plus 9.375 squared. All that into the calculator, we should get a value of 15.625. 0.6 is okay. So this covers the magnitude portion of our problem, but it's also asking for direction. So to get that, we need to get the angle at which it points at. So remember that in order to solve for angles, we need to use inverses. In this case, inverse tangent works. So remember that tangent is opposite over adjacent. So the inverse tangent of our 12.5 divided by 9.375 gives us an angle of 53.1 degrees. So this covers our direction part of our equation. Another situation that you might come across is when two objects are colliding. One is at rest and one is moving, but it's going to collide at an angle that is not direct. So here we can see that when they do come in contact with each other, that they're going to bounce off in separate directions. When that happens, we know that our initial momentum of my object was that only the first object had momentum, not the second object. After they collide, then both objects will have momentum. This object over here is going to have its velocity broken down into two components, a component in the x direction and a component in the y direction. Now, this is going to be important that you remember your vectors. So if it goes to the right and up, it is positive in both directions. If it goes to the right and then down, it is positive and then negative. So remember that you are writing your conservation momentum equations in both directions. So after the collision, our momentum will look like this for both objects. Again, all of these angles are being measured from the line that our first object would have traveled. So that straight line distance all the way through the center. So here we have one angle represented by a theta, and here we have another angle represented by a phi. So this is a Greek letter phi. It's also used to represent angles. If you would prefer to use theta 2 instead, that's okay. Again, our second object is bouncing off, so it has a momentum in the y direction. And then we're adding the momentum of our second object also in the y direction, but this one is going to be negative. So let's look at this example. We have a 2 kilogram mass moving at 5 meters per second in the positive x direction. 2 kilograms. 5 meters per second. In the positive x direction, and it strikes a 1 kilogram ball at rest. Now, this collision is slightly off center. So after the collision, the 1 kilogram ball moves with a speed of 5 meters per second at an angle of 37 degrees below the x-axis. And it's asking for the speed and direction of the second ball, the 2 kilogram ball. So let's start with our momentum in the x direction. At the beginning, we know our momentum of our first object will be m1 v1 naught plus 0, because my second object is at rest, is equal to m2 v2 cosine theta plus m1 v1 cosine phi. Again, all of this is information I know except for my phi and v1. So instead of writing v1 and cosine of phi, I can actually replace this with my velocity in the x direction for my first object. Okay, and that's going to give me this piece, this velocity in the x direction of my first object. I get m1 v1 naught minus m2 v2 cosine theta all over m1 is equal to vx1. Putting all your numbers in, you should get a 3 meters per second. Again, this is my 3 meters per second for my first object, and it's in the x direction. Now we can do the same thing for the y direction. I can say that m1 v1 naught, and actually, I have no momentum in the beginning in the y direction. All of my momentum is in the x direction. So we can start this by 0 is equal to m2 v2 sine theta plus m1 v1 sine theta. Again, very similar to the first part, but I don't know this v1 sine theta, so I can replace it with vy1, and then solve for vy1. So that becomes m2 v2 sine theta. This should actually be a phi, since it's a different angle. All divided by m1. All of your numbers in, you should get a 1.5 meters per second for my velocity in the y direction. Again, that is only this piece. And then what the problem's actually asking for is the velocity. So the resultant velocity in this case. To get that, it is the Pythagorean theorem of 1.5 squared plus 3 squared gives me a value of 3.4 meters per second, rounded. And that only covers the speed portion. I need to go back and find the direction. For that, we can use inverse tangent of 1.5 over 3 gives me an angle of 27 rounded, 27 degrees.